Hello and welcome to the third of the Physics 121 pre-lecture video clips. Today we're going to talk about the application of Newton's second law to a block sitting on a table at rest and to a block sitting on a table inside an accelerating elevator. We'll start with the block on the table at rest. We want to answer this question: what are the forces on the block? So we start with step one. Make a little sketch indicating the situation and indicate the given parameters. So I've got a table with a block M and the given mass is M. Step two. Do we know the acceleration in this problem? Yes, we do. In this problem, what is the acceleration? A equals 0. The block is at rest. Step 3. Draw a free body diagram. So we make a little square for our free body diagram. This is a free body diagram of the block. We represent the block as a point-like object. We use the force menu. Use the force menu. The force menu. Listing forces from the menu, we have weight pointed downward. And we know what the weight is. It has a value mg, points down. The magnitude of the weight is mg. There must be another force pointing up. We know that because there's no acceleration. That we call the normal force. And the normal force in general is unknown. It's a contact force. It's a push. We add a little coordinate system in the corner to indicate the direction of positive motion. Step 4, apply Newton's second law. F equals ma, Newton's second law. In this case, F equals ma is applied in the y direction. So the net force in the y direction is equal to the mass times the acceleration in the y direction. It is important to use the free body diagram to contend with the net force. In this case, the normal force points in the positive y direction, while the weight force points in the negative direction. So we add the normal force, the magnitude of the normal force, and we subtract the magnitude of the weight force. Then we set that equal to the mass times acceleration, which is 0. That means that the normal force is equal to the weight, and we know what the weight is. The weight is mg, so the normal force here is equal to mg. Again, these are the magnitudes of the normal force and the magnitude of the weight force. We now know which way the forces point. We know what their magnitudes are. We know what the forces are. Now let's contend with a different problem. Same steps, but now we have a block and an elevator. Instead of sitting on a table at rest, the block will be inside an elevator. There's an elevator with a cable on top of it. And will be a block of mass m that we'll put in here, sitting on the floor of the elevator. And in this case, the elevator is accelerating upward at a given acceleration, which we will call a. So we know what the givens are here. The givens are the mass and the acceleration. So now we follow the same steps. We contend with the acceleration. We know what the acceleration is. Step 2, acceleration is not 0, it's a. So we keep that in mind. We draw a free body diagram. Again, free body diagram of the block, all the forces on the block. We know that the block is we know that the block has a weight force on it. It always does. And likewise, it's in contact with the floor, so it has a normal force pushing back. Notice that the direction still that we're interested in is the vertical direction y. And when we're done, we have the same free body diagram that we had in the case of the block on the table. In other words, the motion of the block doesn't change the forces. If I have a block sitting on a surface, the normal force and the weight apply just as before. Now we apply Newton's second law. Step 4. F sub y equals ma sub y the same way. This is written down the same as before. Now I should point out You should never skip this step. Always write down F equals ma in the appropriate coordinate, no matter what else you're doing. Contend with the left side. The normal force points up, so it's positive. The weight force points down, is negative, so we subtract. And that's equal to the mass times the acceleration, which in this case is a. So we solve for the one quantity whose value is unknown. We know that the weight is equal to mg still. That never changes. That's always true. So we solve for the one unknown in this problem, which is the value of the magnitude of the normal force. So we say n minus mg equals ma, or n equals m times a plus g. We now know the magnitude of the normal force, and we know the magnitude of the weight. Note that the magnitude of the normal force is not equal to mg. There's no way to calculate the value of the normal force except for applying Newton's second law. The only known force in this problem is the weight force. Once you have that, you can use the second law to calculate the normal force.